Good afternoon, ladies and gentlemen, and welcome to your SETI Institute Colloquium series. My name is Frank Marchis. I will be the host today for this colloquium. So I'm here to I'm here to introduce our speaker, Marisa Palucis. She draws all the way from Caltech today to give us a talk on the work about the Mars Science Laboratory. So let me first introduce you briefly. Marisa received a Bachelor of Science from the University of South Carolina in 2005. She moved then to UC Berkeley to receive a PhD at the Earth and Planetary Science at the University of California at Berkeley, of course. And I found the title of your thesis, which was extremely fascinating to me. Using quantitative topographic analysis to understand the role of water on transport and deposition processes on crater walls, right? So, in 2014, she moved to Caltech to start a postdoctoral fellowship funded by the NSF EAR program. She's a science team member of the Mars Science Laboratory since 2012, so right at the beginning. And today she will basically talk about a work on interpreting the data and the observation of the Mars science, Mars curiosity, and understanding understanding the landing site and the hydrological events within the Gale craters. One note: this talk today is sponsored by Diane and Fred Newman. In memoriam for their song, Rick Newman. Rick loved to attend science talks like this one, and we decided to dedicate this talk to his memory. So, without further ado, please please join me in welcoming Marisa Palucis.
Thank you. So, I want to thank you all for having me here today. I'm really excited to share some of the work that I did during my PhD at Berkeley. My PhD advisor was Bill Dietrich, who's a geomorphologist. And in today's talk, I'm going to be talking about how we can use surface features, so geomorphic landforms, to infer information about past hydrologic conditions. And I'm going to focus today specifically on Gale Crater, which was the landing site for the MSL Curiosity rover. And this was an image that was taken, I think, on April 15th of a sunset from Curiosity on Mars. So that's very pretty. So in process geomorphology, arguably one of the biggest questions in sort of the broadest sense is how can we link climate to process to topographic form? And what I mean by process is what are the physical mechanisms by which we erode sediment and transport it through a landscape to create the landscapes that we see, such as this one here. And we have equations that describe many of these processes, but these equations aren't climate-based, so we can't actually write out a set of equations and from that back calculate out how much water it takes to form a landscape. And if you talk to terrestrial geomorphologists, they're going to ask you, well, why is that important? We have plenty of water here on Earth. Who cares? Well, on Mars, a key goal is to try and constrain the past hydrology and climate. And we have these different features. We have various deposits. This is the Valles Delta. And so it's telling us that there was water on the surface of the planet, but ideally we want to get more information from that. We want to know how much water, we want to know how intermittently it was wet, and ideally we want to know when there was surface water and how much. So being able to do this inverse problem of calculating how much water it takes to form a deposit like this one really will allow us to get at the intensities, durations, and volumes of water it takes to evolve a planetary surface. And so to really do this problem well, you ideally want to have be able to do detailed topographic analysis. You want as much surface data as you can get. And you also want to develop terrestrial field studies that are really addressed at answering this question, because this is something that most field studies don't typically address. And while I'm not going to focus on all of that today, I'm going to focus mainly on sort of the first part, which is using this wealth of topographic data that we have for Gale Crater to try and say something about its hydrologic history. And so a concept that's been introduced in the literature and that I'm going to use here today, especially for the first part of the talk, is this idea of a water-to-rock ratio. And what this means is this is the volume of water. So this would be if you have a catchment, such as this one, and you have runoff over some drainage area, how much water does it take to deposit a feature such as an alluvial fan here? And then while this seems very simplistic, it actually requires a lot of mechanistic understanding of how a landscape works. You need to know how much water and the processes by which you take bedrock and break it down into sediment. You need to understand how much water and the process it takes to transport that sediment and then deposit it into features like an alluvial fan or a delta. All right. So as I was saying, understanding process really is key. And here I have a video from Sue Cannon from the USGS showing a debris flow event in Colorado. And you can see here that you have very large amounts of sediment being transported for relatively modest amounts of water. And so some of the work that I did at Berkeley was really trying to constrain what the water-to-rock ratio would be for these types of flow events, and found that on average you're transitioning from what we would say is a debris flow system to a fluvial system at water-to-rock ratios around 0.25 or 0.35. And then if you go to the sort of other end members, so these high water-to-rock ratios, these are more fluvial systems. So here, this was a video filmed at the St. Anthony Falls Laboratory in Minnesota. And if you look on the bed, you see these particles that are saltating and hopping by. That's called bed load transport. And those have water-to-rock ratios in that very thin bottom layer of about 10. But as you go up into the water column, as you can see, you're much more water to sediment. You're typically only transporting dissolved or suspended load. And so if you sort of integrate over a column of water, your water-to-rock ratios are typically greater than 100. And we have theory and semi-empirical relationships for sediment motion and fluxes for fluvial systems. So especially for lowland rivers, we can calculate when sediment will move and how much will move fairly well. It's not so good as we start to get up into steeper catchments or steeper channels. But for debris flows, we don't really have field parameterized transport equations. And this is actually something that I'm working on during my postdoc at Caltech. So when you look at a landscape and you ask how much water does it take to form, there's kind of four questions or four things that I like to think about. And one is, what's the dominant process? And so here in Gale, we're thinking mainly about, are these debris flow or these fluvial deposits? How much sediment are actually contained within these deposits? Because we're going to use that to then back calculate out with our knowledge of what the process is, how much water it took to create these deposits. Where relevant, we want to be able to apply sediment transport and hydraulic equations. So if, for example, you have something that was deposited by a debris flow, if you apply these sediment transport relations to that for a fluvial system, you're going to actually calculate huge volumes of water to move, say, a large boulder, when in actuality, because it was deposited by a debris flow, much less water was required. So you really want to make sure you're applying the right equations to the right process. And then also thinking a little bit about intermittency and time, which is a really hard kind of topic to address when you're looking at these deposits. So in today's talk, I've kind of divided up into three main sections. The first is to sort of go through what I talked about on that last slide, this sort of step through for the Peace Vallis Fan. And this was a fan deposit near the landing site for MSL. And then take a step back and look at different deltaic deposits or inferred deltaic deposits around Gale, to show that it's likely that several large lakes persisted after that large central mound, which is referred to as Mount Sharp, formed. And this is work that Natalie here first talked about in 1999. Ross Irwin from the Smithsonian Institute also touched on it. So this isn't necessarily a new idea, but we do have, we're getting better and better data with HiRISE and CTX, so we can sort of keep pushing on this question of large lakes in Gale. And then third is to start thinking about, well, what was the source of this water? And so stepping back and looking a little bit more regionally around Gale and other craters in the area. Now, to get you all oriented, So this is a topographic map of, or an elevation map of Mars, and you can see that Gale is located on this crustal dichotomy. So you have in the southern portion of the planet, or the highlands, and then as you go north, you are going down into the lowlands. And Gale is located right on that transition. And Gale has been sort of the most recent date for its formation age. So when it impacted was about 3.6 billion years ago. And this is from various groups of people who've dated using crater counting, looking at the ejecta blanket of Gale. And so if you think about sort of a very broad scale of thinking about Martian climate, you have sort of early on, you have a wetter period of time perhaps it was warmer, and then there's this transitioning where the climate oscillated or it transitioned going from wet to what we have today, which is very dry and cold. And so Gale forms sort of in this, this period of a transition in the Hesperian. And so Facet and Head in 2008, they looked at various, these large valley networks across the surface, and they dated them, again, with crater counts, and found that most of them date to be around 3.5 billion years old, with some, 3.4, 3.7 billion years old range. And this is about when Gale formed as well. So it's likely that Gale formed during this intermittently wet time. And we can see the evidence for this when we actually go in and focus in on Gale. This is a geomorphic map. This was a map that I modified from Ryan Anderson and Jim Bell's paper in 2010. And this is also built on the work, as I said, of Cabral et al. And Ross Irwin. And so you can see here that Gale hosts a variety of different topographic landforms. Colored in tan are small alluvial fans, and colored in blue, which is a little hard to tell the difference between tan and blue here, are delta deposits. You see that there's these valleys or gullies that are ringing the crater walls, and as well as the areas where you see different ridges that might be recording old paleo channels. And first we're going to focus in on the Peace Vallis Fan. And so very quickly, just to make it clear, very simplistic definition of a fan and a delta. So a fan is, as you can see, is typically a sedimentary feature that has that fans out in a fan-like form, very appropriately named. Typically, you have sediment and water that are coming from some upslope canyon. Typically, it's confined, and then when it reaches a valley or a basin below, that the material starts to fan out, spread out, depositing this cone-like feature. And typically people talk about fans as having, that it builds up by a process of avulsion, where you have a river that's moving back and forth, sweeping back and forth, depositing sediment as it's doing so. And this is just a video from a grad student at Berkeley, Alex Brick, and this is a fan in Bolivia. And so you can see, it's a very short movie, but you can kind of see these channels that are sweeping back and forth, and that over time builds up these fan-like shapes. And then we also have deltas. We're going to be talking about deltas a little bit today. And so deltas are when you have a river that encounters a still body of water, so it can be an ocean or a lake. And today we're going to be talking more about lakes. And so sediment's being transported in a river, and then it hits the still body of water, and it begins to deposit out. And so work by Stephen Lay, I'm saying his name right, he's been looking at doing, along with Gary Parker, looking at work with Gilbert Deltas. And so I have a little video showing. So you can see that the sediment is it's coming through this little river. This is a desktop scale experiment, obviously, and you see that this front, these four sets are very straight. And it forms a very distinctive sort of topographic form that in the geomorph literature is often referred to as a Gilbert Delta, after G.K. Gilbert. So focusing in now on this Peace Vallis Fan, this was right near the landing site. So this is Bradbury Landing, which is where Curiosity landed. This is a elevation map. So red is higher elevations, and blue is getting into lower elevations. This is a fan. This was originally traced out by Anderson and Bell using thermal inertia data, and then I sort of independently mapped it using the topography, and they lined up, about the same. So this is sort of the consensus on like the Peace Vallis Fan form. And you can see here, though, that the most distal part of this fan is dipping into a topographic low. So if you follow this white line here, this is an enclosed basin. So if you had water, the water would stay in here, you'd have a lake. And it's going into this very low portion. And when we sort of showed, working with the team when we first landed, the fact that we were so close to this topographic low, such that if there were water in Gale, if there were any size lake really, this would have been the last place that water would have remained. It would all drain to this point. And so that, combined with all of the excellent mapping that the MSL team members did prior to landing using orbital images, where we saw very cool different contact between 3 different units, sort of led everyone to decide that we were going to go, as many of you know, that we were going to traverse east first, and before heading to our actual destination, which is Mount Sharp, which is south of the landing. And so when we went and we traversed to the east, we actually landed down in here where the arrow is, and it's referred to as Yellowknife Bay. And that's where we found lake deposits. And so this was a topic John Grotzinger wrote a paper about the stratigraphy and the sedimentology there. And this was very exciting for all of us, because this is something that the geomorphology really sort of predicted in combination with the mapping, that the orbital mapping that we were all working on. And so in studying these deposits, this is where we did our first drill site. This is where we found clays. I don't know if you guys follow the Curiosity saga is the right word. So it was very exciting a couple years ago, but it also led to a lot of questions about where the sediment came from, how old the sediment was, and what the hydrologic conditions were when this sediment was deposited. And so this is something that I spent a lot of my time as a team member working on. And so the idea, something kind of the big question was, well, how much water does it take to build this fan, and what was the source of water? And so first we want to know, as I've talked about earlier, what was the dominant process? If you're going to get anywhere near the right order of magnitude estimate, you want to know, is this a debris flow or a fluvial fan, because both exist here on Earth. We want to know how much sediment. Since we're doing these water to rock ratios, it's the volume of water to volume of rock, so we need some idea of the volume contained within this fan. Intermittency, so we want to know how often was this fan continually active. So was it built up pretty quickly, or was it active for a short period of time and then inactive? So how long did it take to build the fan? And then once we kind of have an idea about the process and the size of the fan, again, applying what we know from sediment transport, and then using that to calculate water amounts and what implications that has for the hydrology and even climate. So the first question was, this fluvial or debris flow dominated? And so I spent a lot of time mapping these small ridges on the fan. We identified 43 different, which we infer to be paleo channels. This is based off of, we can see layering in these channels. They're also perpendicular to contour, which is where you'd expect water to flow. We see that they're weakly sinuous and discontinuous. We don't see a lot of branching on the fan, and that's something that we do see a lot on terrestrial alluvial fans. You see these branch channel networks, and that's often because of rain falling, on the fan, not just water being supplied from upslope. We found the average width is about 30 meters, which is pretty appropriate for a fan of this size. We also don't see any indication of debris flow deposits. So we didn't observe any levees that you might see associated with debris flows, or lobate snouts, which are often sort of indicative of a debris flow fan. And when we plotted, so this is looking at this is distance. This is going from the top of the fan down to its toe versus elevation. Actually, this is for just this channel. It's not the entire fan. So it's just looking at the long profile of this upper channel here. We can see that it has a concave shape. And in fluvial geomorphology, that is associated with river systems. Well-developed river systems often have a concave up profile. And the slopes, so we calculated slopes about every 100 meters and then averaged it over a 10-point moving window and plotted that here. And the slopes range from about 1 to 2.5%. So while it doesn't seem like a lot, if you ever like set it on a treadmill, 1%, you can barely feel it. But for a river, you can carry pretty large size material. So this is what on Earth where gravel bed rivers lie. They lie in this 1 to 3% sort of regime, and they can carry material that's pretty decently sized. And so this sort of led us to the conclusion that this is likely a fluvial fan based on the fact that these are pretty low slopes, the channel morphology that we see. We also found at the distal end of the fan these fluvial gravels. So this was work that Rebecca Williams led, as well as work that Eileen Yingst did. And so Becky looked at the conglomerates along the traverse from where we landed to Yellowknife Bay. And her analysis of these conglomerates was also that these were fluvially deposited. And she shows a nice image in her paper looking at one of the outcrops, the Link outcrop, and comparing that to a fan deposit that's in the Atacama Desert. And so then, sort of going from there, we want to know now how much material is actually contained in this fan. And so it's easy to get the area, map out the shape of the fan, and it's in ArcGIS. It gives you the area. You really need to figure out how to get this third dimension. And so what we did to make an estimate of this, and this could still obviously be refined, but we took sort of the topography of the crater walls and we extended that underneath the fan deposit. And we looked at different possible morphologies of the crater wall. One would be that the curvature continues underneath the fan and has more of a realistic crater shape. The other is perhaps that it is flatter. And so in doing these different topographies, we create essentially a pre-fan surface. And then we difference that with the actual current day topography to get a total fan volume. So we calculated this is a pretty small deposit. It's about 0.7 cubic kilometers. But we also need to account for wind erosion. So it's a windy place on Mars, and these deposits are very old. So a lot of this sediment is being eroded by wind and saltating sand particles. And so we wanted to know, well, how much material are we losing due to this type of erosion? And so what we did was we mapped various sort of remnant deposits that perhaps are preserving the older fan surface on this lower portion of the fan. And in HiRISE imagery, you can see this deflation of this lower fan surface. And so what we did was we essentially projected what the topography of the upper fan was, projected that out to points in this lower area where we think are recording sort of the pre-eroded topography to reconstruct a pre-eroded fan topography. And then we difference that with what we see today to get at an estimate of how much material has been removed due to wind. And so we found that that's about 0.14 cubic kilometers. So about 25% of the fan volume has actually been eroded away. And this is just looking at the fact that there's also been some deflation on the upper fan because we see those channels. So they're inverted channels, which appear as you sort of erode away the floodplains and you leave sort of the gravel in the center that protects the material underneath from eroding away as well. And so that is another couple meters of material on the upper fan. So it's all said and done, the total pre-fan volume is about 0.9 cubic kilometers. And something that I didn't show in this talk, but is that we actually checked that with the upslope drainage area. So ideally, you'd want some sort of constraint on this number because you want to know, well, perhaps there was a lot more erosion that happened that we're not taking into account. So we looked at the valley network upslope of the fan, and it was about 0.8 cubic kilometers. So there's a fair correspondence between the amount of material that was removed from upslope and it's deposited in the fan. And so then we want to know, can we make some estimate of the discharges that it took to build this fan? So we know the channel slopes and we have some idea of the channel width, but we need to know a grain size and a depth. And so what we do, these are kind of basic equations in bedload transport and geomorphology, looking at basically assuming a threshold channel. And so what we do is we know on terrestrial rivers, depending on the relative amount of sand to gravel, what the critical shear stress is. And it's typically between 0.02 and 0.06. We also know that for most fans and many gravel rivers on Earth lie between about 10 and 100. So that's the ratio of the channel width to the channel depth. And so when we do that, we can use equation 1 to actually calculate out what the predicted grain size would be. And it's about 30 to 1,000 millimeters, so that's about a meter. And we actually do see in the HiRISE imagery, we see boulders, meter scale boulders on some of the channels high up on the fan, and we see in Becky Williams's work looking at those conglomerates, some of the largest classes she looked at were about 40 millimeters. So it's in the range of sort of what we actually can observe either from imagery or from the rover. And then from that, we can use the law of the wall, which is an equation to calculate velocity, and as well as conservation of mass. And in doing that, we find that for a range of pretty plausible conditions, so a fan slope of about 2%, we would calculate discharges between 4 and 200 cubic meters per second. Now, we wanted to think about sort of the possible sources of water. So this is the drainage network that I told you that's feeding this fan. This is where I calculated the volume of material that approximately equals the volume contained within this fan. And you can see that the tips of this drainage network go very high up. This is the crater rim, so we're going high up past the crater into these sort of plains. So for groundwater to have gotten that high, it's pretty unlikely that this was sort of a groundwater-fed fan. And as I said, the fact that we don't see, though this could be a preservation issue, but the fact that we don't see really branch networks in those inverted channels on the fan itself seems to argue against rainfall as well. And so one possible source then would be snow. And so I think I may have talked through these as a snow source. And this is something that Edwin Kite, he has a sort of a snowmelt model that he came out with in 2013. And what he did was he assumed a set of conditions. So he had a pure CO2 atmosphere, dusty snow, and he had a faint young sun. And so for certain obliquity conditions, you get this band of where snow would be stable on the surface of Mars. And within that stability zone, you also have, at the same time, you have areas where you could actually also melt that snow. So you need both. You need snow to be stable enough to form a snowpack, but then you need to be able to melt it to provide the runoff that you would need to build a fan. And so he predicts that for Gale, for various portions of its lifetime, if you will, you could get snowmelt rates of about 1 millimeter per hour. And so if you take that over the entire drainage area, you would get about 200 cubic meters per second. Of course, this is assuming no losses. This is assuming no sublimation or infiltration. But that's approximately the discharges that were same order of magnitude that we're getting from our analyzing the channels on the fan. So to get at this sort of idea of timing, which is very difficult to get from just looking at a deposit. Here on Earth, you can go out and do cosmogenics or OSL, and you can look at the actual stratigraphy, but we can't really do that unless we turn the rover around and go up north, which I don't think we're going to do. So one way to do this is to think about what if we had a sort of a one M-member case of how long one M-member case where we're going to ignore sediment supply or water limitations. So we're basically going to say we have a big pile of sediment upslope of where the fan is. So we have infinite sediment supply. We're not worried about water needed to break sediment down from, say, the crater rim. And we're not worried even where the water came from. We just know that we have infinite supply and water. And what we want to do is then calculate how long it takes to deposit the total volume of material that comprises the Peace Vallis fan. And so we have equations for sediment flux, as I mentioned, for gravel-bedded rivers. So we can use an equation like this, and we have to assume a grain size. We have to assume a channel width to depth. But in doing that, we can then calculate the time it would take to build the fan. So you just divide the fan volume by divide the fan volume by sediment flux to get out of time. And so what I'm showing here are, in this plot, so this is transport stage. And so what this is that it's the critical shear stress. So there's some shear stress that you need to move sediment. If you're below that shear stress, so if you don't have, you're at low flow in a river, nothing's going to move. And so then you're going to be in this sort of domain. And then there's that critical shear stress. When you're at that critical shear stress is when you start seeing particles wanting to move. And then as you get above that, so as you get higher discharges or flooding events, then you might be several times above the critical shear stress needed for particle motion, in which case you're going to have high fluxes of sediment. And so here in this plot, this is transport stage. So this is just dividing the actual shear stress divided by the critical. And so when you're higher than 1, this is where you can move large amounts of sediment. And here we had to assume, so I assumed a range of grain sizes based on what we saw in HiRISE. So, if it was, the whole fan was consisted of meter-sized boulders, which, I don't think is true. We wouldn't be able to deflate the distal end if it were, or if it was smaller, gravel size. And we could see that the time to build this fan, and again, this is assuming kind of continuous conditions and very ideal conditions that we often don't have here on Earth, is you would need 10 to the 6 to about 1,000 years to build a fan that's the size of the Peace Vallis fan. And then from these calculations, you can back calculate out what that water to rock ratio is. And so it's, as I said, anywhere from 100 to 400. And so another way to think about this is instead of assuming this sort of ideal fan case is to say, well, what do we see for terrestrial rivers, since we can observe those today. And so this is a compilation that was done by Savitsky and others in 2003. And so they looked at 293 different rivers from around the world. And in taking their data set and sort of plotting it in this water to rock ratio, which isn't really a concept you hear about as much in sort of terrestrial geomorphology, but when you sort of plot it in this way, we find that for these, I call them intermittently effective rivers, because most rivers are below transport capacity most of the time, and it's when you have these larger events that you actually are able to transport sediment. And so for these sort of more real rivers, you get water to rock ratios, an average about 10,000. So very high, so a lot of water to move not so much sediment. And there was a smaller study that was performed by Pepin et al. In Chile, which is nice because they looked at unvegetated rivers in Chile. So this might be a little bit more similar to what we would see on Mars, since you're not thinking about the influence of vegetation. And they found that their water to rock ratio is about 5,000. So if we sort of plug in these numbers for our fan, if we do this sort of idealized case where we have a hose that's we're blasting a pile of sediment for as long as it takes to get our fan built, we would need about 400 cubic kilometers of water. If we use this number from Pepin, this sort of perhaps a more realistic terrestrial analog to the Peace Vallis fan, we would need about 5,000 cubic kilometers of water. And if we do sort of the average for the terrestrial rivers of the world, we would need about 9,000 cubic kilometers of water. And so when you take the catchment area of Peace Vallis, which is about 730 square kilometers, and divide that by these volumes, you would need anywhere from 500 meters to 12 kilometers of runoff. And so you definitely need, if this is how much water it took, you would need a hydrologic cycle to build this fan. So you can't store this much water in one go and sort of rapidly melt it and form this fan. And sort of an illustration of this, so this is a long profile of Gale. So this is going from the north to the south, and this is elevation on the y-axis. And so here is that central mound, Mount Sharp, and these are the crater rim, and here's our little Peace Vallis fan. And so if you need several kilometers of water, you would basically have to store water higher than the central mound as a snowpack or something like that. And this, again, is not taking into account the fact that typically when you have runoff, you're losing some of that runoff. It's not all being used to transport sediment. A lot of this is getting evaporated or infiltrated or even sublimated. And so this really argues that you would need a hydrologic cycle where you would build up more realistic amounts of snow in the catchment, melt that, build a fan, and that would continue for some period of time. So the conclusions for the Peace Vallis fan are that this was a fluvially constructed fan, and this is based on sort of the morphology of these channels and its low gradient. Debris flows typically can't run out to gradients this low. They'll typically deposit at steeper slopes. The fan is composed of about 1 kilometer or 0.9 cubic kilometers of sediment, and about 25% of that has been eroded away since by the wind. If we assume sort of ideal conditions, then it would take thousands to about 10,000 years to build this fan. And for such a small feature, it would require a lot of water. So you would need some hydrologic cycle in the post-Noachian, so in this Hesperian age, to really build a feature like this. If it works in a similar way to it does the way we think about it here on Earth. Now, as I mentioned before, Gale hosts other depositional features. So the Peace Vallis fan, we spent a lot of time thinking about because this is where we've actually collect data from the rover, but has been pointed out in the literature, there's other forms, other fans, and other deltas. And so I'm going to look at 3 different systems. And the first is this, what we're calling the Fairivalice system. And so here, this is, again, one of those, it's a sort of an elevation map with, I don't forget, 20-meter contours, I think. And we can see here, this is the crater rim, up here in red, the highest point. And there's this Fairivalice, so this channel that cuts into the rim. And over here, we have an arcuate deposit. And I'll show you better images of these in a second. And then you have over here this second deposit that is perhaps a delta. And then on top of this, if you can see these convex contours, these are very indicative of alluvial fans. They have those, there's that cone shape in the topography. And so this is the first Pancake Delta. This has been identified by many people in the literature. This is about 100 square kilometers in area. And this ridge here, it's pretty consistently about 250 meters high. And similar features have been seen elsewhere on Mars. This is an image from Martin Kleinhaus. And so using CTX data to create a DTM, you can see that there's right along the entire rim of this, this pancake-shaped feature, you have, it's running along a similar contour. So I've highlighted this 3280. This is all from HRSC data, the contours. And then plotted a long profile. And you can see it's a little exaggerated, but you have here these lower slope top sets, and then you have this sudden increase in slope as you come over the edge, similar to that movie I was showing you earlier from Stephen Lee. And then it meets up again with the topography. And obviously, as we get better data here, if we had HiRISE data, we can make much better topographic maps, and also see if we see channels on this feature. We don't see them in CTX. Now, if we kind of follow this orange contour around, because one delta point, you can argue, well, maybe it eroded back to that point, that this is sort of an erosional scarp now. But we do see that if you follow this HRSC contour around, we have this very small feature coming out of a canyon. This is the central mound, which looks perhaps to be, again, this is very coarse imagery, so you can see it looks like channels on this, and this also, again, this front runs along this contour. You can also see this was mapped independently by Ryan Anderson, and I put his channels on here, and you can see that these channels sort of, these blue channels seem to all stop at this orange contour line. And again, if you were to follow the topography, if you were to put water on any of these points, it would flow out. So if water came off of Mount Sharp, it would flow down into this lake or into this basin here. And then this basin actually drains. Would be draining to the west. And so, and this is again in this image here, so this is draining to the west, and this would be it would be draining this way. And again, this is higher in elevation. This is going down into sort of the lower portion of the northern crater. And we have this second potential delta feature. And so this here is a long profile going down this, what we're calling this Fairivalice Delta. And so you can see here again, you have this fairly continuous top, and then it sort of transitions all of a sudden and then meets up again with the base topography. And if you take this and follow this contour around the crater, you actually can trace it to this second area, which we're calling a western delta. And you can see here this is the same contour. It's matching up with these small little delta-like deposits coming off the western crater, the western rim of the crater. And this again here is going, this is a long profile going from A to B. And so you're going down. You can see this is that where this front is, this steep front, this matches where that other front was on the Fairivalice Delta. Oh, so this is something that's starting to be, people are starting to think about more, which is the fact that we're seeing these in many places on Mars, these stepped deltas, and we want to know what this means, because it could be that it's a backstepping feature, and so what that would mean is there's this second front, and so if you had, say, a lake here, you'd have sediment that's depositing and dropping out and forms this delta here, and then if the lake level were to rise, the sediment would then start dropping out sooner, and it would give you a step-like form. And so that would be an indication that you actually have perhaps lake level rise. And for lake level decline, so if this deposit, as water declines, if it declines slowly enough, you'd expect to see gullying into these deposits. And we don't see it at the level of CTX imagery. That doesn't mean that if we had, say, HiRISE of these deposits, we might see more. To tell more about this relative, whether or not you have a lake level rising from or a lake level decline. And so we're going to now follow this yellow contour to what we're calling the entrance canyon deposits. And this is exciting because this is somewhere we're actually going. So this is the distal end of the Peace Vallis Fan, which we talked about earlier. This is where we landed, and this is our traverse over the past almost 3 years now. And this is sort of where we're at today. I think this was like Sol 950 or something. And I think we're at like Sol 990 now. But we're kind of just driving around this little area, so we haven't moved much. But the goal eventually is to cross these dunes and get into, people have talked about a hematite ridge, and then getting up into this canyon here. And so we're calling this the entrance canyon. And this is a really gorgeous image that Tim Parker made. And what he's been doing is he's been taking the HiRISE elevation data, as well as HiRISE imagery, as well as images that we're starting to get from the rover, and sort of combine them all into one image. And so you can see this deposit that we're going to be driving to, and they have this flat sort of base. Some people call it the washboard. And then you have this weird sort of thin deposit that's coming out of this. There's a little gully, and then it's coming out of this canyon. And so this here is this is the sort of the canyon, and you can see that you have a lot of infilling and material, and then it transitions into what looks like this gully. And then that transitions into this series of deposits. And something that we really want to see with the rover as we're getting closer is whether or not these are also, one, delta deposits, and two, if they're stacked on top of each other, which again would tell us something about the lake level history here. And so you have these four very distinct deposits. We have this bottom deposit, which I'm calling deposit 4. Overlying it is this more lobate-shaped deposit, which it's a little hard to see. You can see it in this image here. These thin, which again are running perpendicular to contour, suggesting these are channels of some sort. And then you have this larger deposit I've outlined in red, and a very thin, perhaps, fourth deposit in green. And based on the HiRISE imagery, it's a little hard to tell still. It'll be better as Curiosity gets closer and we can image this. But these seem to be distinct deposits that are stacking on top of one another. And so here is a long profile going from the top of this first deposit in green down to this last deposit onto this washboard. We know sort of what the boundary would look like underneath these deposits because we have the topography of this washboard, but up in this region, we don't really know. So this is sort of an unknown lower boundary. But again, you can see that here at this red arrow, we have what looks like a delta front. And again, here at this orange. And this orange actually corresponds to the yellow contour from the western delta. So we again have another sort of correspondence of deposits where these perhaps delta deposits seem to be corresponding to the same contour line, which would mean that if there were a lake there, that this material would be depositing at the same time. And so these, unlike the Peace Vallis Fan, where we've talked a lot about it being a fluvial system, these deposits are much steeper, and they appear to be much coarser. So you can see the boulder, it's very bouldery in the HiRISE imagery. And so these are perhaps debris flow, these were perhaps built from debris flows coming down. And so at the last AGU meeting, I talked with a student of Martin Kleinhaus, who's been actually doing some desktop scale debris flow experiments, where he's been looking at, as you alter sediment concentration and water and clay amounts, the different types of deposit morphology that you would get. And he has this little video where he's showing, this is the first deposit that came down, and you can see how it comes down in a very thick sort of tongue-like fashion, and then the second deposit sort of comes over it. And you can see this is somewhat similar to what we're seeing in the entrance canyon deposit, where you had that long first flow that came out that was highlighted in yellow, and then you have these flows that don't quite go as far out the next time. And granted, this is a desktop scale, so there could be some scaling issues, but it's interesting to think about, and this is something that we can actually test with the rover as we get closer, which is exciting. And I also want to point out that this same front that we see in this entrance canyon deposit corresponds to also the transition in these there's several large canyons coming off the central mound, and there's a transition from, you see, perhaps small delta-like deposits at that same elevation. And so what this suggests is that there were perhaps 3 lake stands in Gale Crater. So you had this high lake stand that is most noticeable by this pancake-shaped delta, but that we see a correspondence of the termination of channels as well as a small delta here. So you would have had material being deposited both from the crater rim as well as from canyons coming out of Mount Sharp. And then you had this second lake level that's probably most easily defined by, you see the Western Delta and the Fairivalice Delta, and then you had this lowest lake level defined by the entrance canyon deposit front, these very small deposits coming out of these canyons on the western side of Mount Sharp, as well as the lower portion of the Western Delta. And so if these are recording past lakes, this Pancake Lake would have had a depth of about 700 meters and would require about 3,800 cubic kilometers of water to maintain. This middle lake would have had about a mean depth of about 400 meters, about 16 cubic kilometers of water, and the smallest lake level would have had a mean depth of about 300 meters and a water volume of about 900 cubic kilometers. So, and this is all since these deposits are also coming out of Mount Sharp, so these are canyons that have already been developed, and these smaller deposits are coming out. That mound was already there, and we're then cutting into and depositing sediment from that mound. So these are not these are lakes that came after Mount Sharp was already sort of at its current form, which is different than some of the press releases where we're driving through now what also look to be like perhaps delta deposits that are much lower in elevation and perhaps are associated with actually building the mound. And so some testable hypotheses that curiosity can test. We have this small steep sequence of deposits that's spilled out of this entrance canyon, which we're hopefully going to get to. These slopes deposited, or the depositional slopes, are about 10 to 20%, and they have an abundance of boulders, suggesting that they may be debris flow dominated. At least one stage of deposition has a steep, sharp front, and this front corresponds to other steep, sharp fronts that are perhaps deltas around Gale Crater. And our observations, based on remote sensing data, hypothesize that we can actually, if these deposits are from, these are stacked deposits as I was talking about, if that's the case, then perhaps these are actually recording a lake level rise. And this is something that we can test, again, with curiosity. But I want to note that we do see incision into deposits that are associated with that Pancake Delta and the Fairivalice deposits, so suggesting also that there was a falling lake level. And so the idea is to think about what sort of sequence makes this all work. And I have one hypothesis that I'll show in a minute. But it suggests that at least there were 3 large crater-wide lakes, or at least 3 lake stands, after Mount Sharp reached its current form. And I talked a little bit about sources of water to Gale. So we have these deposits. We obviously have that large canyon, Fairivalice, that's feeding in, that would have likely fed a lot of water to Gale Crater to supply to these large lakes. It's possible you could have had some regional groundwater flow. As you can see, Gale is, if you were to say follow this bottom of Gale and the bottom of Gale, it's on there's a regional gradient as you go from the south to the north. So perhaps water would have followed this gradient and provided some of the water, at least, for these large lakes. It also suggests, this is the line shown for that Pancake Lake, so that was the largest lake that we talked about, that the orange contour defined. So you would have had water on both sides of Gale, and perhaps would have saturated some of these, would have saturated the deposits of the mound. And these are deposits that we're going to be exploring with curiosity. And so something else that I spent a little bit of time doing in this idea, thinking about where water came from, is this is a sort of a zoom back version. This is Gale Crater. This again is the crustal dichotomy. And you can see here every number corresponds to a valley that's cutting into either a crater rim or into the crustal dichotomy. And if it has a pink number, it corresponds to an alluvial fan at the end of that valley. And if it has a purple number, it corresponds to a delta. And if it has a blue number, then there's no deposit associated with that valley. But you can see that these valleys all seem to be oriented in the sort of southeast direction, south to southeast direction, suggesting perhaps that there was some either regional groundwater flow or runoff running from the north to the south. And the Gale is part of this more regional story. The two that are sort of really outliers, though, are the Peace Vallis Fan and this western delta. And the Peace Vallis Fan, I forgot to point out earlier, but it is much lower. It's on the floor of the northern floor of Gale Crater. So if it had formed prior to these large lakes, it would have been submerged under those lakes, or it perhaps formed after these large lakes ended. Which is our sort of current favorite hypothesis, because we don't really see any incision or lake line or shorelines into the fan. But again, it could also have been eroded away, or if there was not a lot of wave action in Gale, it might not have cut into the fan very much, and perhaps we wouldn't see it. So these are just sort of things to think about in terms of where the source of water to Gale Crater was. It seems likely that it would have come from the south. And so I have this just quick one possible lake sequence based off of the deposits that we've been looking at, which is you have this, this channel network that pre-existed. This is work that Ross Irwin showed that then got disrupted by the Gale impact. So you have Gale with its perhaps a central peak, and then over time it was Mount Sharp built up. And this is sort of then of zooming in of the crater. This is now we have Mount Sharp at its sort of close to its current topographic form, and that some point perhaps that drainage or that network to the south of Gale got reactivated and started to cut the crater rim and deposit the sediment associated with the Pancake Delta and some of the sediment that's been is comprising the Fairivalice Delta. And then if those deposits are recording some sort of lake level rise, in order for the entrance canyon deposits to deposit and step back, there would have needed to have been a period where this lake would have declined below the level of the entrance deposits and then started to rise again. And so you would have this intermediate lake level where you built up the western canyon deposits as well as that lower entrance canyon deposit. And then you'd have a continued lake level rise where you build the rest of this Fairivalice Delta, as well as the top stage of that Western Canyon Delta. And then perhaps that after sort of the period of large lakes is when you would have deposited fans like the Peace Vallis Fan and these very small steep fans on the northern rim of Gale. We're not really sure about this guy, but if there was a period of sort of drying and no longer water in the crater, this might be when you would deposit these fan-like features. And the main reason for suggesting that fans came after the deltas and the lakes, one is there is a fan that you can see on top of this delta here, which I've colored in, as well as the fact, like I said, we don't see any evidence for incision into these features due to a dropping lake level. Okay, so in overview, really quick, we see that in doing these sort of analyses that at least the Peace Vallis fan would have required some hydrologic cycle to build a fan, and it could have lasted for thousands of years, which isn't an absurd amount of time. These deposits in Gale likely are recording a period of large lakes after the central mound, and knowing exactly what that lake level sequence is something I think that we're really going to test as we get to this deposit, this entrance canyon deposit, and the fact that it seems that there is a potential water source feeding Gale from the south to the north, and that's perhaps also responsible for the incision of other crater rims throughout the region. And so I just want to thank all of the people I get to work with on MSL. They're amazing, as well as Alan Howard's group at University of Virginia and Jeff Moore and Orkin for getting to talk about alluvial fans, and then my PhD advisor. So thank you.
Okay, the floor is open for questions. We have already two over there.
You showed one picture of a fan that looked like it had a lot of craters on it, and I was wondering, is there any way to know when the water went away based on the craters that you see on top of the fan?
So that's something that I really spent a lot of time trying to figure out, because these features are very small. They're only 80 to 100 kilometers, square kilometers in size. So then you're doing this crater counting on very, very tiny areas, which sort of messes with your statistics in that you can't really get big, even if it's an old surface, you can't really get the big craters that you would need to say that it's older. But people like John Grant have done like creative things where they sort of look at all the different features in Gale. And so he's sort of led the work on doing crater counts of these different deposits. And he did the one I think you're talking about. He looked at the craters on that Pancake feature. And he gets that they might be pretty young. They could be, you know, a billion years old. It's pretty young, but so that's some of the work he's been doing. So, but I mean, even he says usually when you talk to him, you have to take it with a grain of salt because they're such small areas.
Hi. You've done some impressive work with terrestrial analogs for these kind of things and looking at the fluvial fan and all that. I'm wondering, one slide indicated that the atmospheric pressure of the Hesperian was about like 1/10 of a bar, something like that. But the main difference would be the gravity, like it's, you know, just a little over 1/3 of our gravity. Does that have a significant effect on the shear strength or any of the other properties as compared to the terrestrial models that you're using, or is it basically not going to affect the way the water is moving and its ability to move deposits?
So when you kind of go through the whole like scaling arguments, looking at settling velocity, flow velocity, the shear stress to pick up particles, when you do those sort of analyses, gravity typically cancels out. So it doesn't seem to be in that way a huge issue. The other sort of maybe somewhat comforting fact is that these deposits that we're seeing, the deposits that deltas are depositing on Mars and that fans are depositing at, are the same slopes that you see on Earth. Same with debris flow deposits. People have done a lot of work with gullies, looking at debris flow deposits, and I've done similar work at Meteor Crater, and so it's the same. The deposits seem to be in the same, like, depositing at the slopes you'd expect to on Earth, at least. But yeah, so at least from like simple, like, back of the envelope calculations, I think if you'd really want to be sure, maybe you'd want to go into do some of these experiments, which would be super cool. And you know, when you see these people doing like these desktop debris flow experiments or looking at delta, doing it in maybe a reduced gravity environment. But of course, then you're also dealing with scaling issues because you're doing things that are really small. So I'm not super worried about that as being like a major. But yes.
Do you have an equation for this wind to rock ratio, and also what size rocks are you talking about?
So yeah, so I think when you see this water to rock ratio, that's what I was saying, is that you can calculate from sediment transport. So we know if you have a low sloped river, and you know it's just at the simplest level, it's the total volume of water you would need to deposit some volume of sediment.
Can you write this
It's not a equation per se. It's more of a definition. And that's what I'm saying. You really need to understand the mechanics and the equations that you need to understand sediment transport, and that will tell you, let's say, the volume of water it takes to move a certain flux of sediment, and then you can then ratio that, and that's the water to rock ratio. But this is just something that people tend to do, I think, because it's an easy way to think about, do you need a lot of water or do you not need a lot of water? And I think there's a lot more complexity in that, and you know, that's sort of what I tried to do here. Instead of just sort of making up a water to rock ratio and saying, oh, it's this number, is going through the actual sediment transport equations and then calculating the total amount of water that you need to move a certain amount of sediment. So it would be the sort of, the slide that I was talking about, sort of the ideal fan. If you have that case of a big pile of sediment and you're bringing water to it, those sort of equations for sediment fluxes and discharges basically are all tied up in that water to rock ratio concept. But we don't have that for debris flows, really. That's something that, like I said, I've done some experiments looking at different mixtures with different amounts of water and different sediment concentrations, and you can measure metrics that tell you about this is a debris flow, or this matches what people see in the field and this doesn't. But there's not a nice set of equations where you can say, this is how much water it takes to entrain and develop a debris flow and deposit it. So that's kind of a big open unknown still.
So what's the source of the snow that you think is feeding, that fed the fluvial fan in the Gale Crater? And also, what does that imply for what the thickness of the Martian atmosphere was at the time that this was happening?
So some people have suggested, that you could have lake effects, that you have these larger lakes in Gale, and that you then deposit, or as you have, waters evaporating and then depositing as snow along the rim, that you would have to, again, there'd need to be some issue with the timing there, because the alluvial fan that formed, I don't think formed into water, or at least if it did, it formed into a very small body of water. It's distal, not into a large lake. In terms of atmospheric pressure, I mean, based on, I'm not a climate modeler, but what Edwin Kite looking at, I forget his numbers, but in his model, he's able to generate snow and snow melt with fairly reasonable numbers. So, but yeah, I'm not sure.
Could the permafrost have melted as a source of water, and does that change from season to season on Mars? Because these fans formed over many years. So many
Yeah.
cycles.
Yeah, and that's something that would be interesting to think about is, because people talk about if you have, say, an impact nearby, you have localized heating for a while, and that could release water, or increase ground temperature, and you can melt permafrost. And again, we don't know, like the water. It seems to be morphologically a very fluvial fan, so you definitely need more water than you would need for like a debris flow. Whether or not it was on that lower end that we estimated of like water to rock ratios of 400 versus 10,000, then I think that would change whether you can do this with like permafrost melting or not. But it seems like you would have needed, and especially because that upslope, the catchment that you're seeing, if you go upslope of the fan, you do have an incised valley. So you have a valley that's cutting into, it's like 100 kilometers long and in places several kilometers deep. That's cutting, a canyon. So you do need some amount of water to do that cutting. And so I don't think, really slow trickles of water are going to do it.
Okay, before we let you go, as a memory of your talk here, you have this amazing cup showing two robots talking to each other, and that's a kind of
so
a
cute.
souvenir for the SETI Institute talk. Thank you very much
Awesome, thank you.
for being here.
Thank you, guys.